Okay, so cross-classified models. So when you learn multi-level modeling, you start off learning two-level analysis, students within schools. You then extend that to students within schools, within school districts, a three-level analysis, and you can keep on adding levels easily enough. But your data structures, I need a microphone. Do I need that again? I took that off when I was eating my sandwich. The data structures are often more complex than two or three level hierarchies. So a classic example that we'll look at here is that we observe students and they're clustered by the schools that they attend. Simultaneously, students are obviously living in different parts of the city, in different neighborhoods, and there are neighborhood effects if students are simultaneously nested within local neighborhoods. But not all kids from the same local neighborhood go to the same school. There might be an element of school choice going on, for example, and not all kids in a given school come from the same neighborhood. So we don't have students within local neighborhoods within schools, okay, and we don't have students within schools within neighborhoods. Rather, we have two separate two-level hierarchies operating on the data at the same time, and we want to take both into account. We do so with a cross-classified model. So that's what we're going to describe here. Example, Scottish neighbourhood study. There we go. So we're the studies, the two examples before the lunch were new lectures that I've made for this course. These two after lunch are ones I've given before. And I hadn't really so I've got to be a bit careful here. We'll have to see. Oh dear. Okay. Oh, sorry, but I'm going to go through obviously the cross-classified model. One thing I do need to talk about is notation of equations. Why? Because if you look at different textbooks like Snyder's and Bosker, or by York Hawks or Stephen Raudenbush, they use different notations. Yeah, and it's very confusing. Likewise, the journal articles, and particularly the American educational researchers write down the models one way, the Europeans write it down another way. And different software are kind of requiring you to think about models in different ways as well. So I'll go through the notation that has been used, which is slightly different, because essentially your IJKL is the hierarchical notation, which breaks down once you have cross-classified and multiple membership type data structures. But we'll also revisit topics like variance partition coefficients and interclass correlation coefficients. How do you calculate those when you have cross-classified data? And then you might think, as always I do this, can I get away with ignoring the plausible values, ignoring the weight, ignoring the cross-classified? What happens? So we'll look at that. And then we'll even look at something which is quite nice with these models, a random interaction classification. We're going to have random school effects influencing students' outcomes, random neighborhood effects influencing student outcomes. But might not there be interactions between which neighborhood you live in and which school you attend? Okay, such that it's the combination together gives you higher or lower than what you'd otherwise predict. So non-additive effects of school attended and neighbour lived in. Okay, so a better example might be a cross-classified, so students age 16 test scores. We nest students within the secondary schools, but we also take into account the primary schools. Okay, and the primary school effects, which are long-lasting on student outcomes, the secondary school effects. But might there be something about the combination of a primary and secondary school that matters? Some might be really good, reinforcing combinations, teaching styles complement, and others might clash. The primary school really did think in a certain way. You went to a secondary school and did things in a completely different way, and that ultimately gives a negative interaction. So there can be interactions between effects, between random effects, just like they are between explanatory variables when entered as traditionally with regression coefficients. So that's kind of a nuanced idea. It's quite interesting. So we'll look at that. Okay. So here we go. Scottish study. Gone in Raudenbush. There we go. So Stephen Raudenbush, I think, visited Edinburgh a long time ago.
I wasn't here.
No. So clearly, probably in the 80s, late 80s. And he is the most prominent traditional multi-level modeler from the States, kind of education sociologist, but very much a statistician at the same time, and a very nice textbook. And he's obviously analysed these data. And I think on the lemma, you might have seen the lemma training materials we have an online course, and I think I have a cross-classified session in there. And so I've reanalyzed the data essentially as well. Okay, so it's a very simple analysis on the data, which aren't particularly strong data, but they serve well enough for a teaching example. And sometimes when the data is a bit shaky, it actually shows up kind of issues which can arise, including estimation issues. So in some ways, it's actually quite good teaching example. And in a way in which it's shaky is we've got data on 2,310 students. They're only from 17 schools. Okay, so multi-level models, the more clusters, the better. 17 is not much at all. Yeah, you saw PISA had 471. That's really healthy. 17, a bit borderline as to whether you'd do a multi-level model. And then we've got 524 local neighborhoods. These are obviously smaller entities. So the data might be quite close to a 3-level hierarchy, students within very small neighborhoods within larger groupings of schools. But, you know, it clearly departs from this.
Can I ask you a question about this?
Yeah.
Because a lot of the international kind of comparison are country as one level, and often we're talking about small numbers, in terms of 15 to 20.
Yeah.
Would you be against having actually, you know, the multi-level framework with what are the downsides?
Well, the downsides are that, you know, if you only got 20 countries, you are, and you're doing an analysis where you're pooling all those countries in and allowing country random effects and so on. You're doing it ultimately because you probably want to add in some country level explanatory variables, and you've got very little power. So if you've got 20 countries, it's like you've got a sample size of 20, and you're trying to relate country GDP to mean test scores or whatever you're trying to do, you're going to struggle to estimate those effects as significantly unless they're very large effect sizes. And you're clearly limited as to how many country variables you can put in. And that between country variance will be estimated quite erratically. And that can throw things around a little bit as well. So it's not that you can't do it, you just need to be aware of those stresses and to communicate that and caveat your results. Yes, with Mark Bryan from Essex. Yeah, that's nice. And they might look at different methods as well, kind of cluster robust standard errors, economists fixed effects, and and I remember that.
I understood who does multi-level modeling. I did something with the Asian barometer survey, and again that has, I think, 17 or 14 countries in this way. And what I was told at the time was, well, if you are finding looking at various partition coefficients, if you are finding that the countries have a significant amount of variance in them, then that's okay. The problem is that it might not detect the variance. It might not detect variance with such a small number of level 2 observations. But if you are finding variance, then it's present. That's okay. But would you agree with that?
Yeah. So I mean that parameter, the between school variance, is identified off 20 countries, so it's going to be estimated imprecisely, have a big standard error, and so it's not a reliably estimated parameter. But that parameter affects the standard errors on the GDP. In particular, so it's just the knock-on ramifications around the model. There's different schools of thought. Andrew Gelman, who's really a very prominent statistician and who does some applied work in political science, he quite merrily kind of does things like age categories as random and ethnic groups as random, which most people wouldn't treat as a level ever, and they have a very limited number of categories. But when you're very prominent, I do what you like, really. So he's just rebelling against everyone else, against perceived wisdom. So but often in textbooks you often see, you need to have at least 20 clusters. It's not a clear-cut number. The fewer you have, the weaker the analysis.
Only an example then, if you have a small number of clusters and there is evidence that there's variation going on, you say that it's erratically estimated. But is it better to have the label to allow for more accurate standard errors than.
Yeah. I mean, you might, I mean, and even one of the difficulties is if you do something like cluster robust standard errors instead, which is an alternative approach for dealing with clustering, that also breaks down when you have a few number of clusters. So, you know, one of the alternative methods is, you know, it's still good to compare across methods, but all these methods struggle. You know, you could put in country fixed effects, but then you can't put in GDP, which is your research question. So you just have to do the best you can, try different variants, explain what's going on, explain the weaknesses. That's just the nature of the data. The data are what they are. So yeah, there's just some caution, I think. Okay, so we've got an attainment score of national examinations in Scotland in the 1980s at the end, age 16. Whoever knows about that, that's what we've got as the dependent variable. And in the kind of analysis that Garner and Radebush were doing, they're relating to students' kind of socio-demographic characteristics, their earlier prior attainment, has a value-added flavour to it, presumably some school and neighbourhood characteristics as well. It's just a small teaching data set. So let's have a look at it. So this is a unit diagram. These are quite useful for trying to communicate to an audience or yourself the mechanics of the data structure, particularly as the more levels you have, the more cross-classified and multiple membership it is. So in this one, what I've drawn here is just 12 individuals or students, okay? And I've just illustrated how the first three are nested in neighborhood 1, students 4 and 5 in neighborhood 2, and so on. So it says level 2 here. So neighborhoods are at level 2 in the model. Students are at level 1, but we simultaneously have another level 2, if you like, or another set of clusters operating, which are schools. And so children's 1, 3, and 5 attended school 1. So not all kids from neighborhood 1 go to the same school, because student 2 goes over here. And not all kids who went to school 1 came from a single neighborhood. So this is what I'm saying. We neither have students within neighborhoods within schools, nor do we have students within schools within neighborhoods. We've got two parallel two-level hierarchies operating on the data at the same time. And so we need to do something slightly different to account for that. You might have other examples. I mentioned the one with, this could be students within primary schools and secondary schools. We said that one. But you might have, it could be scores. So these could be scores on, let's say you've got 50 essays and 20 raters. And every essay is scored by every rater. Or maybe every essay is scored at random by 2 raters, double marking. This could be an example of testing their marking procedures and benchmarking before they do proper marking. That's cross-classified as well. Or you might have students' responses nested within items and nested within students. Okay, so that's cross-classified. And in macro kind of studies, often in the states where they've got long panel data on states, you might have the state year measurements, the GDP in Alabama in 1972. Okay, you've got every year, every state. And so those data points are nested within states, 50 of those, also within 40 years. And they're treating years as a level. So you can like, right? And you can see all these different examples, but that's also a cross-classified model. But the point is, once you learn cross-classified model, there's actually many different applications. Whilst we're focusing on a specific one, there are many others that you might consider. So let's look at the data. Here we have, I've written higher level IDs. These are both kind of operating, if you like, at level 2. We've got school ID and neighborhood ID. So here are 4 students in school 1, 4 in school 8. Within school 1, we've got 2 kids from neighborhood 139, but neighborhood 139 also supplied the kid to school 8. And this is the breaking down of the hierarchy. So you can see it. You can see what I was depicting visually and saying in words. You can see it in the data just by staring. Here is the student unique identifier, the 3rd column. Here is the dependent variable attain, which has been standardized. It's a Z-score, so it's got mean 0, standard deviation 1. So 1 unit difference in the dependent variables of 1 standard deviation difference. So that's quite nice. When we do regression models, the coefficients are going to come out in effect size metric or closer to it. Our level 1 covariates are characteristics of the students, your reading score at age 7, or probably in year group 7, I would have thought. So the start of secondary schooling, because the outcomes at age 16. This is for a year group 7 in your age 11, 12. Here is a dummy variable for whether the father's employed. Yes, no. And we've got a neighborhood level covariate, which is the deprivation score, how deprived the neighborhood is. So a trivially simple data set with a few example variables to illustrate mechanically how to do these models. Okay, so one thing you might do is, and this is for pedagogic reasons really, is you might put on the y-axis the age 16 score, the x-axis the schools, and there's some very faint dots here in the background, which are the actual student scores. And you can see just about, they're pretty lumpy. Yeah, 1, 2, 3, 4, 5, 6, maybe there's about 10, 11, 12, 13 unique values. So you'd want to know something about the nature of the age 16 exams, which would lead it to such a limited number of unique values. We're treating it as continuous in our models. The thicker black dots are the mean scores, the observed mean scores for the schools. Now, as soon as you see differences in the school means, we know we have clustering by school. Yeah, the bigger the differences between school averages, the more similar the students appear within their schools, the more correlated students are. But there's only 17 of those schools. Here we do exactly the same in terms of the other classifying factor, neighborhoods. And here we have 524, so they're very small clusters, and we see a lot more variation across neighborhoods. Now, partly that's due to the size. The smaller the group, the more variable they'll be. If these were local neighborhoods and we had more regional neighborhoods with a smaller number, you'd see less variation. So it's a part of it. This is a kind of an artificial thing due to small cluster sizes. But we want our model to account for both sources of heterogeneity, because both of them are inducing similarity in the students' outcomes. So, and substantively, school differences reflect both selection effects. Kids are not randomly assigned to schools. There's some pre-existing differences across school cohorts at entry. Some schools are in more advantaged areas, some are in more disadvantaged areas. But obviously, after 5 years of schooling, some schools are more effective than others, and that will be a second source of influence. And you can say the same about neighborhoods. People select into neighborhoods, not at random, okay, and then their neighbors have different cultures. So it's very hard to, ascribe meaning to school effects and neighborhood effects. They're picking up multiple things, and you need to be very clear about that. Here is a useful way, again, of looking at the data. I've done basically a crosstab of schools by neighborhoods, and I've just, so it fits on the slide, restricted it to one small bit of the crosstab, schools 6 to 9, and neighbors 502 through 512. And the cells indicate the number of kids in that combination. So what you see straight away is that many combinations have no kids. So school 7 had no kids from neighborhood 502, maybe that neighborhood's on the opposite side of the city. Okay, so it doesn't sound. But school 7, maybe it's located over, closer to these neighborhoods who are all sending some kids to it. So we call this a sparse cross-tabulation or matrix. Now, if you have data on students' responses to items on a test, and you have 20 items and 50 students, and every student marks every item, every cell has 1 in it. Yeah, every student does every item once, and there's no kind of missing data, and it's balanced. Okay, so this is unbalanced and it's sparse. So these have implications for the results and how you interpret things. So it's quite good to stare at this. Now, interestingly, some cells have what you might call replicates or multiple students. So here we've got 4 kids in that school by neighborhood combination. Now, what that means later on is we are potentially able to look at not just school main effects, one for each row. Yeah, some schools have higher scores than others. Not just neighborhood main effects, column effects, but we can actually pick out cell effects, which are like the interactions, because we can decompose these four kids. How much of their mean score is due to an interaction effect, and how much is, and what kind of unique variation you have from that. So that's going to bring in this exciting idea of interactions between schools and neighborhoods. And you can see that the data, in theory, support it because we've got replicates, at least in some cells, but these are small numbers. I suspect they might fall over. You've also got a sense of which models might struggle. So the more you know your data, the more you can understand what you can do with them and why models do work or don't work or how to interpret them. So here is a bit more on that, because I want to know, well, how many of these cells have 1, 2, 3, 4 kids? This is slightly different. Just descriptive statistics, so sentences you might write into your paper. So the 17 secondary schools drew their students from as few as 11 neighborhoods to as many as 92 neighborhoods. So maybe, you know, one school's on the outside of the city, so in the study, there's not many neighbors, other one's bang in the middle, 92. But these are characteristics of schools which are interesting about diversity of intake as well. And then from the neighborhood perspective, these are tiny, right? And they've only got a couple of students each. So they're not going to send to many schools in general. And we see 309 or 59% of these neighborhoods were sending all their kids to one school. But in the study, they might only have had a couple of kids. You know, so it's not that meaningful. So that's like a neighborhood schooling model, where all the kids from the neighborhood go to a single school. But we've also got an element, you might say, school choice, because lots of neighborhoods, nevertheless, 40% of neighborhoods in total are sending to 2 or more schools. So yeah, you might be talking about, these might be the substantive things of interest in the background. Now, one thing which is quite cool, and again, it's just mucking around with the data, we're going to say this is a cross-classified data set. Yeah. But, you know, neighbors are pretty small. 60% of them are sending to one school. You know, it's not that far removed, surely, from a 3-level hierarchy of students within neighborhoods, within schools. But to what extent has that been broken? Yeah. It turns out only 14% of my students are, if you like, breaking the hierarchy. If we artificially changed the school attended of just 14% of the kids and said, well, you know, you could have gone to your local school, then that would have been a strict hierarchy. So a statistic like this could even be a kind of a measure in your data, because you might have not just this study in one city in Scotland, but might be all different cities around the country, of to what extent are schooling systems neighborhood-based or school choice-based, and you could be deriving a statistic like this. From a multi-level perspective, it means that, well, if I fit a naive 3-level model of students within neighbors within schools, my answers are going to be fairly close to the correct answers from a cross-classified model, because the data aren't really that cross-classified. They're only a mild departure from a 3-level hierarchy. So again, that will help us understand our results later on when maybe I show a naive 3-level model. Okay, so we're going to shift into the models now, but you hopefully get a sense of the data. And yeah. So here is the model, and also some new notation that I was warning you about. So the first model is just going to be a variance components model, and these models simply say to what extent does the variation in the outcome, in this case age 16 test scores, to what extent is it between schools, to what extent is it between neighbors, to what extent is it left over, residual variation attributable to the student. So this is like, what is the relative importance of schools versus neighbors versus students in terms of overall variability? Okay. So it's just a regression model of attainment scores as a dependent variable, regressed on an overall intercept, the overall average attainment score in the data, plus a school random effect, a neighborhood random effect, and a student residual. And so these random effects and residual have standard normality assumptions with means of zeros, constant variances to be estimated, and the relative magnitude of the school, neighbor, and student variance answers those questions about relative importance. Okay. So that all sounds standard. What's different is the notation. So I haven't used IJK notation because that's kind of strictly hierarchical. The I's are within the J's are within the K's. Okay, so a notation which has been used in quite a few articles and is closer to a kind of R-like notation that Gelman uses is like this. So you have these subscripts, and that's the name of the school variable, school ID, and then in brackets I. So the idea is if you plug in I, the student number, this function returns the school number. So that would then tell you which school that student went to. And if you plug in the value I here, this mathematical function returns the neighborhood that child goes to. Okay, that's how you read the notation. This is the neighborhood So this here is the neighborhood random effect for the neighborhood that student I attended. Okay, that's the notation they use. I mean, I think just use IJK notation and just have one sentence which says this does not imply a strict hierarchy. And we have unique neighborhood IDs, unique school IDs, and you're done. I think that's much simpler. But you'll see quite a lot of journal articles use this notation. They were trying to kind of get a new notation which could be used for all data structures. But I think ultimately, keep it simple. Okay. So, and this is me just explaining, you plug in student 1, and then the function spits out which particular school they attended, 5. Yeah, you plug in student 1, which neighborhood did student 1 live in, 17. Okay, they're like lookup functions mathematically. Okay. And then once you know that, you can write this down, for example. So the attainment score for student 1 is equal to the overall mean plus the school random effect, and the student went to school 5, plus the neighborhood random effect, and they went to neighborhood 17, and it's student 1. So I just say use I there, use J there, use K there, and just say it's not a 3-level hierarchy. Okay, but just at least you know now when you read some of these papers, this notation, it makes it look like a completely different model. It's not. Okay. It was well-intentioned, but ultimately unhelpful. Okay, often you'll see these kinds of diagrams for data structures as well. So this was a unit diagram earlier, drawn in terms of the individual data points for 12 students and showing their nesting. A kind of a shorthand version of that, which is sometimes done as this, called a classification diagram. And so the idea is that you can see students are nested within schools and they're separately nested within neighborhoods. If you have school districts, you have students within school districts. Okay, so it's a way of trying to write down a complex data structure efficiently. Okay, because you might have students, secondary schools, primary schools, neighborhoods, families, school districts, all this kind of complexity with the kids changing over time. And then you can draw it down like this, and it's a way that academics have used to communicate data structure. And show this is the data structure, and this is what actually fits. Yeah, so you'll see that in journal articles as well. Here's one of these mechanical diagrams for trying to kind of show how the model works. So the y-axis here is your age 16 score. I always like to pretend that the data point in question is my own child, because it's very high up the score distribution. So here's my child, they're amazing. Yeah, look at how high their attainment score is. But how does the model get to my child? Well, that's a question of how does the right-hand side work? Well, first of all, if you ignore everything, you're starting at 0. Okay, so let's add on the first thing, beta 0. That takes you up to the average attainment score across all students. And that's this horizontal line. Now, we could add on the school effect. My child goes to school 5. In general, kids in school 5, this is the mean score of kids in school 5. Okay, so adding on the school random effect will get me up to here. Forget schools for now. Now consider neighbourhood 17. That's where we live in Bristol, and that's also got a positive effect. Okay, so not only does my child go to a school which is above average, we live in an above average neighbourhood. Okay, so you start off for the study-wide average, you add on the neighbourhood effect, ignoring school, and you get to this point. Okay. Now, of course, my child lives in neighbourhood 17, so they get that. And they attend school 5, so they get that. You add those two arrows together, you get this big arrow, and you get up to the line up there, which is the average scores implied by the model for those kids, and there's several of us, who live in neighbourhood 17 and go to school 5. So my child and a few of the neighbouring kids. Yeah? Neighbourhood in common, school in common, you get up to that horizontal line at the top. And there you can see them 1, 2, 3, 4, 5 students, and within that cell, which is a cell of that cross classified table, my one's the best. Yeah. Okay. So you can see the model is clearly, it's an additive main effects model. We've got the main effect of school 5, my child gets that. The main effect of school neighbourhood 17, my child gets that. They get added together, we're up to there. It's additive effects. So that's hinting that, well, hang on, maybe I need to allow for an interaction. Yeah, maybe that horizontal line should actually be higher or lower than where it is currently. Okay, and I can bring in, and I will bring in that flexibility later on. And that could be interesting, like I said, with primary schools, secondary schools, clash of cultures, if you have a story for it, and if you have variables to predict it and explain it, so you can really give it that meaning. Okay. So we're going to fit the model. So yes, there's only 17 schools, so we're going to estimate the between school variance imprecisely. Okay, we don't have much data, but the positive is, if I wanted to predict scores for a particular school, I have lots of data points per school. So I've got an imprecise between school variance, but I do have precision when making school-specific predictions. Neighborhoods are the other way around. With 524 neighborhoods, wow, huge sample size, I've got a really precise between neighborhood variance. I can really describe inequalities in my study, but I make terrible predictions for any specific neighborhood because I've only got 1, 2, 3, 4 data points. Okay, so there are different implications going on. Okay, so estimation. So by default, we kind of use maximum likelihood estimation for multi-level models. And that's what we'll use here in the slides. Actually, I'm going to use something called REML. So it's a slightly geeky thing is, if you're doing a 2-level multi-level model, students within schools, you use maximum likelihood. But if you have a very limited number of schools, you switch over to something called restricted maximum likelihood. Why is this? The maximum likelihood estimates, in particular the between school variance, is biased downwards. But that bias is trivially small in big samples. If you have a small sample of schools, the bias becomes noticeable, and you switch to REML. Okay, so people often say when you have, let's say, 40 clusters or fewer, switch to REML. I've only got 17 here, so I'm going to switch to REML. And you can switch it on and off in Stata or not, and you'll see the difference. Okay, that will convince you that, oh yeah, ML is biased down. The REML estimate's always high. Okay. Yeah.
So is it a REML better also when you have pure units, even if you have like pure units within the
Yeah, and I don't think that matters so much. I think it's all about the number of top-level clusters. And indeed, in R, REML is the default. Stata, ML is the default. Different software got different defaults. So you need to know about this, because if you can go across packages, you need to understand why results change. Okay, so if you have 400 schools in PISA, you would notice. Yeah, if you have 20 schools, you would notice. So here you try on the practical, try switching it on and off. I put REML on, which is the better, but try just taking that option off. Okay. So that's one issue, okay, which applies just for 2-level analysis. Now in cross-classified models, there's another issue. Cross-classified models are computationally harder to estimate in terms of estimating equations than hierarchical models. Okay. Traditionally at least. R is amazing. Okay, so Doug Bates's LME4 LMER package, wow. They've done some really clever things. You can fit very large, complicated cross-classified models, and it's super quick. Stata, what you have to do is trick the software to get to fit the model, fit the cross-classified model. The trick is really clever. I'll show it to you, but it's computationally slow. So if you've got a big cross-classified data set, you're not going to be able to use Stata to estimate it. Here it's small, at least you need to have at least one of those 2 levels to be small. Yeah, so schools are only 17. Neighbors can be as big as you like, because at least one of them is small. Okay. But if you have 524 neighbors, 416 schools, this is going to be pretty slow to estimate. So as models become more complex, sadly, you do need to know a little bit more about estimation options, different defaults and different packages, different implementations of cross-classified models, always fast in R, can be very slow in Stata, and so on. And there's another estimation approach you would shift into. When maximum likelihood starts to fail, you then shift into MCMC, Bayesian estimation. I'm not going to show any of that today. Markov chain, Monte Carlo methods. Okay, you can do it in Stata, you can do it in R, for all these multi-level models as well. But just be aware that sometimes you're forced into doing that because it works better for more complex models. Okay, right. So here, look at that. Is that horrid? R users. Who are the 2 R users? You can put your heads on the table. You do not need to look at this slide. This is for Stata users only because you have an excellent implementation of cross-classified models. Stata users, this is what we're going to have to do. Okay, now, as always, you know, the notation, the syntax in Stata will allow you to specify it easy enough, but you're wondering sometimes it looks pretty weird. Why is it slow this time? Why is it fast that time? This is why. Okay, this is the trick. The trick is you need that strictly Stata and the mixed command can only fit strictly hierarchical models. Okay. For hierarchical data. We don't have that. We've got cross-classified data and a cross-classified model. So we need to reparameterize our cross-classified model to be a constrained hierarchical model. And then Stata will go, oh, it's a hierarchical model, and I can deal with constraints, we're away. Okay. This is the trick, and it's really nice. Okay, so we've got students. We've got students within schools, we've got students within neighbours. Yeah. And all of this is within Scotland. Okay, so let's forget the schools for now. We've got students, yeah, 2,000 of them within 500 neighbours within country. Scotland, there's one of them. Okay, so our 3-level hierarchy is students within neighbours within countries, and our 3rd level has 1 unit. Okay, that's the first thing to do. That's a strict hierarchy. It sounds pretty weird because we've only got 1 unit. So the IJK notation that I've used here is student I within neighbour J within country K. Yeah. That's the first thing you do. And then we've got student residuals. That's fine. Students are nested within neighbourhoods. We've got neighbourhood effects. Good. So how do we get the school effects? This is the bit in red, which is what looks weird. You put in a school dummy variable for each and every school. And there's 17 of them. So you have 17 dummy variables in the model, but you do not estimate their regression coefficients, because that would be an economist fixed effects approach, a dummy variables approach. So we're not doing that. Okay. So there's no betas on these dummies. Instead, what we do is we make them random at level 3. Yeah. What is level 3? Scotland. Okay. So V1K, V2K up to V17K, these are 17 school effects, 1 for each school, but they're random effects. Yeah. And the K subscript is always Scotland. So the V1K, there's only 1 value there. Okay. You'll do this in Stata, right? And this is what it does. Okay, so why does this work? So that V1K, V2K, all the way up to V17K, well, here they are, written in terms of my distributional assumptions. There's 17 of them. Okay, well, here we go. This is why it's slow. We've got 17 random effects, not 1. And so we estimate a 17 by 17 covariance matrix. That's huge. That's why it's slow. And then here come the constraints. We constrain all their variances to be equal. So the common school variance, that is the 1 parameter we want. So we've got the 17 by 17 matrix. We constrain all the diagonal, the variances to be a common value, all the off diagonals to be 0. This is why it's grossly computationally inefficient. But that's a 3-level model. Okay. And that will give you identical parameter estimates to Doug Bates' fancy, really decent approach, right? And if you, as long as one of your clustering factors is relatively small, you know, 17, 50, whatever, it works. And then the synthesis, some Stata syntax, and it will just go. So that is what it's doing. And the other reason why this is important is because whilst in Stata, you just specify an option and it'll do it. When we come on to multiple membership models, there is no option. So you will have to manually do this and then manually do these multiple membership weights for pupil mobility. So this actually, so you do need to know this for the next session. So sometimes you might think, you know, just tell me the Stata options, right? I don't need to know the detail. You need to know the detail because there's no Stata option in the final session. And this is your starting point. So that I appreciate that's quite complicated. It's really, it's very clever. It's a 1994 paper. We did it, they did it in Emma Wynne, and then Stata copied it. And then Doug Bates just wrote a better algorithm, which didn't require any of it. So, yeah.
So if you have 100 schools,
you'd have one, you'd,
100 dummies.
yeah, what 100 dummies. And then you'd have a 100 by 100 covariance matrix where you put these constraints on. So you're only trying to get one parameter out of that, but it's got to be inverting this matrix, and so that's why it's slow. And so whichever, so schools and neighbours, whichever one has more units, you put here.
Yeah.
Yeah. If you do it the other way around, then it's slower. Now maybe in the file I did it both ways around. You go, oh, that was really quick, but that's really slow. Yeah. So you do it like this. Yeah. Really clever, and some of you mentioned sibling data. So, and there's some multi-level papers with sibling data, which bring in things like ACE models, like genetic effects and environmental, shared environment and unique environment, and those do really kind of fancy things, tricking software to kind of estimate the genetic variance components, environment, really nice. So, and if you want to do things like dyadic data analysis, that's very complicated as well. So this is where the data points are on. There's a variable. How many words do we speak to one another? Okay, we have one dominant person. So how many words do I speak to you? How many do you speak back? These are dyads. Okay, and that's got all kinds of clustering because we've got individual effects with an outlier. Okay, and then there's a correlation between how many words I speak to you and speak to me, or these correlations, dyadic correlations. But you can, once you realize it's a framework and you can go off piece, you can build custom models in standard software, station and R, for doing what you want. And then it's kind of becomes a little bit, oh, I did a methodological innovation. And you can do it within standard software. You know, there's limits. But yeah, this was an early example of doing something really kind of clever. Okay, so this is neighborhoods. This is where I did it the other way around. Look at that, 524. That's slow. That's much slower. Don't do it that way around. Try it, and you'll see. But if you hadn't looked at this slide, you wouldn't really kind of get that necessarily, right? So here we go. So we fit finally model one. Ooh. Model one is, and all models are fitted by restricted maximum likelihood because we've only got 17 schools. If we didn't do that and we did ML, then that estimate of the between school variance would be downwards biased. Possibly there's an appendix slide showing that. You can try that. Model one is, well, model two is the model of interest. Okay, model one is only there to provide a change in deviance, which gives me my likelihood ratio test for showing that model two is preferred to a model which ignores clustering. Okay, that's why I do that. So model one is really just a linear regression with no explanatory variables. And what do we get back? A mean of 0 and a variance of 1 because the outcome is z-score. So substantively, it's of no interest whatsoever, but it gives me a deviance, a fit to the data. Model two is where we add in two things. We go, what? No, we can't do that. You're going to have school effects and school clustering, put in school variance. You're going to have neighborhood effects, neighborhood clustering, put in the neighborhood. Deviance drops by 210 points. And that's a big drop, big likelihood ratio test statistic, 210. And so it's statistically significant. Model two is statistically preferred to model one. And often you want to justify the complexity. So you've got to do these likelihood ratio tests. So that's the only reason model one's in there. So I could get this out. It's a drop. So substantively, if you look at this, we know that the variance in the outcome is about 1. So you can see what we got here. We've got about 80% at the student level, roughly 20% at the aggregate levels. Okay, so there is clustering in the data. It looks like neighbours are more important than schools, but bear in mind these are smaller entities. Okay, they're more bespoke, so you're going to see greater variation and huge clusters where everything just gets averaged away. Okay, so you've got to bear that in mind when we're making these descriptions as well. Okay. But that's model two's cross-classified model. So in terms of the results, just interpret it kind of in the usual way. It's just how do you get to that point? Then you might do things like, can we ignore the neighborhood effects? So just see what happens if you ignore the neighborhood effects. Model two is one we just looked at. You get rid of the neighborhood effects, some of the variation comes down and it gets misclassified as student variance. We're overestimating student differences, if you like. Some of it goes up to the school level. Okay. more of it goes down a level because we're quite close to a 3-level hierarchy. In strict 3-level hierarchy, you ignore this level, it goes down in its entirety. Most is a bit unbalanced, a little bit goes up, most goes down. Okay. So because neighborhoods are neighborhood variation mostly within schools, because we're fairly close to students within neighborhoods within schools, not totally, but fairly close. So you understand where the variation goes. Okay, and a likelihood ratio test, now the deviance goes up. Deviance is bad, yeah? Badness of fit. So this fits worse than that, and that differential is 85 points. So we prefer this model to that one as well. We're just justifying the variance components as we go along. And you go, well, okay, so George says I can't do a 2-level model of students within schools. I know, I'll do a 2-level model of students within neighborhoods. Model 4. Now here, because neighborhoods are fairly close to being within schools, all of that school variance comes down and it gets described as neighbor variance. Okay, and very little of it comes past that to the student level. Okay, so if you did model 4, you'd be saying, hey, neighbors are really important. Yeah, but we've ignored schools. And part of what you're calling neighbor to neighbor differences, that's actually better described as school clustering, school differences. Schools play a role in student attainment. Yeah, so and of course, even in this model, we're missing out all kinds of things. We're making all kinds of assumptions. So trying to be transparent about what you're not doing in your modeling as well. Right. And that is also statistically preferred. So we've really shown we've got 2 sources of clustering. Both are separately statistically significant and they're substantively meaningful in terms of the magnitudes of these variances. Okay, so that is what I'm just showing here. I'm simply showing, and you could see this already really, because in this model, those 3 variances pretty much add up to 1. So just by eyeballing it, I can go, oh, about 8% between schools, about 14% between neighbours, about 80% the student level. Here, I just did those calculations formally. School variance divided by total, student variance divided by total. And because the total adds up to about 1, they're coming out basically the same. But if we hadn't standardized the outcome, you'd have to do this step because it wouldn't be so easy to calculate. Okay, so what else can you do? You can do residual diagnostics, which we've not really said much about. In the PISA data, we're not trying to make statements about individual schools, and indeed they warn against that. We haven't done this so far. But in this kind of study, maybe you do want to say something. Maybe it's closer to a value-added study where the whole purpose is to estimate individual school effects for accountability, choice, improvement purposes. So, so with residuals from a multi-level model, there are 2 purposes. Okay, residual diagnostics, which is to check the model assumptions. So here these are quantile plots. Just do it, if you don't like this, just do a histogram. Yeah, histogram of the school residuals. Does it look normally distributed? Yes, no. Yeah, I know it's a bit loose, but if something looks grossly skewed, you might transform the outcome, or there's an outline, you might take out, that one. Neighbours as well. Both those look pretty normally distributed, good enough for me. In quantile plots, you want them to line up on the straight line. If you don't like that, do a histogram, you want it to be a line on the normal curve. So that's the traditional, that's what we always do with residuals, even in linear regression. But in multi-level model, the cluster effects are also substantively interesting. Okay, and can be the motivation for doing the analysis. So the top plot are the 17 predicted school effects from the model. Okay, and we've put 95% confidence intervals. Those are tight 95% confidence intervals, but each school is large, has many students. Yeah, neighborhood differences, even though the neighborhood variance is bigger in general, which means the point estimates, they vary more on the y-axis than the school ones. So even though the bigger effects are more variable in general, individually, they're estimated less precisely because we've only got a couple of students per neighborhood. So we're seeing now the consequences of the descriptive statistics and understanding the data earlier on. Many clusters means probably I'm going to get more variation because they're more bespoke, but I'm going to have a lousy job at predicting any individual one. And pretty much every single neighborhood overlaps with the 0 line. So I can't use this to kind of as the basis of going into neighbors and asking questions or doing follow-up things because there's not enough precision. There's a lot of chance variation. But at the school level, there are significant differences between schools, and including individual schools appearing significantly different from other ones. And we could use that top plot to go into schools. But those school differences, that's not necessarily that school quality, very much going to be selection effects, and we need to adjust for baseline differences between schools. Okay, so just again, be careful about the interpretation. But we can do this after adjusting for covariates equally as well. Okay, so this is, I'm now going to introduce the random interaction classification. So remember, that was where I said, look, I can cross-classify students by schools and neighborhoods. I observed that many combinations have no kids, but some combinations have 2 or more kids. And as soon as I've got 2 or more kids, at least in some of those cells, I can try and estimate school by neighborhood unique interactions, which would allow, for example, the prediction for my child who goes to our local school and lives obviously in my neighborhood, and there's several of these kids, maybe this main effects model is not adequate. Maybe there's some interaction departures such that the mean score should actually be lower than that or higher. Okay, and there could be some substantive stories to tell about that. So how do we bring that in? Okay, so I guess a few more stats here. 91% of the cells are empty. Okay, because clearly if you live here, you don't go to the school miles away. So most combinations of neighbours and schools have no kids. It's only when neighbours are close to schools that they're going to send the kids to them. 3% only include 1 student, and only 6% of the cells include 2 or more students. So I showed you a small snapshot of the cross classification where there was lots of data. Many snapshots would have no data at all. Okay, which is telling me I'm going to struggle. Whilst this is substantively interesting and reasonable models to specify, my data is not going to support it. Okay. You're often in that. Often things that you want to do by theory, you can't do with your data. So we can do it in principle, but I'm worried that I might run into convergence difficulties.
What level would you say is generally good? Like, so you said 6% fair.
Yeah, well, that is a methodological PhD chapter, simulation studies, not some guidelines. If you're doing what's the relative importance of schools, neighbours, families, you know, and with cross-classified models, interaction things, that's the methodological factor. So, yeah. But you don't see many applications with these interaction classifications, but you can easily come up with interesting substantive stories. And obviously then you could look, well, we know that the school climate in the primary school, we know the school climate in the secondary school, same climate, they differ. How divergent are they? Does that predict the interaction? And then you've kind of got an explanatory model for those interactions. And that's, yeah, I'm not really seeing that kind of stuff. So, yeah. But this is mechanically how you put in the interaction thing. So here we've got our fancy notation. So you generated a new variable in your data set, which is a unique ID for every pairwise, every combination of school and neighbour you observe. There can be lots of those, yeah? And many of them are going to have only 1 kid, okay? And that goes in as a new level of analysis in the model, and another random effect. And here I've estimated it, and that's model 5. And the nice thing about this is that in Stata, it's really easy to estimate because it's going to come in here. Because we've got IJK, student I in neighbourhood J in Scotland. So where does a school by neighbourhood cell come in? Well, they're nested within the neighbours. So it's a new level here, it becomes a 4-level model. Students within those cells, within neighbours within Scotland. So it's no more complicated for Stata to estimate. And it continues to be easy for our estimate. Yeah, so it's going to get inserted here in terms of this kind of trick we have to do. And it comes out, oh, it's quite big. Okay, 0.068. Okay, so the school main effects are about 8% of the variation. The neighbourhood main effects are 9% of the variation. The school by neighbourhood interactions are about 7%. Okay. And this has mostly come from the neighborhood variance. That's the one which has dropped and been reapportioned here. Okay, a little bit of that came up here as well. Is it statistically preferred? Pretty borderline. Deviance drops by 4.14. That's my likelihood ratio test statistic of change. And that's got a p-value of just under 5. This is a tiny data set, so I don't find it very trustworthy at all. But mechanically, this is, yeah, something you can do, and I've illustrated it here. Yeah.
Is there a way to interpret or think about the fact that when we look at the variance of the neighborhood, it dropped more. So basically the interaction ate more from the neighborhood level variance rather than from the school level variance. Despite being an interaction between the two. So if there's a story we can tell.
So I think this could again be related to the fact that there's so many more neighborhoods than schools. So again, this is something that you could study with simulation studies to try and work out what you can and can't take from these models. Can we get the insight, the full insight that we want, or are there restrictions? So I think you'd always expect that in the setup where you've got 500 neighbours and only 17 schools. But then what are you kind of really estimating here? It's driven by the sample sizes rather than the substantive phenomenon of interest. So I think you'd want to have some kind of critique of that. This is team paper, right? Yeah.
I have to say, I didn't believe the actual estimate for school variance because it's usually higher, and usually the other way around. It's higher school level than neighborhood. Yeah. So as soon as I saw that, I thought, okay, that's the problem with the number of cases we have at each level. Yeah. No, I agree entirely. And you can see the kind of the naive t-test on the school variance. This is not estimated with much precision, which means that number could be all over the place. This is the number we observe here, but yeah, just bouncing around over. So yeah, so mechanically I'm showing you things, but it's on such a small data set that from the start I'm a bit like, but if you did this with administrative data, then maybe it could be more interesting. But yeah. But even if you conclude that's all a bit dodgy, that's an interesting methodological paper. Because you can do these things, these are the natural interpretations you jump to, but let's write a kind of, these are the warnings against this, and here's an interesting thing which shows, yeah. But these are the kind of stories people tell with these models and data sets. Finally, we're just adding in explanatory variables, and so the complexity is always the random part of the model. Adding explanatory variables is kind of easy, interpreting them is pretty easy. As well, not ignoring important concerns around confounding, of course. But essentially, here I've added in attainment 5 years earlier, so we expect a strong positive coefficient of beta 1 because it can be highly predictive of later attainment. Here's dad's education. The dad stayed in school beyond 15. Here we expect a positive coefficient. Those kids whose families had a father who has more education, well, that is positively predictive of their own education. And when we adjust for these student characteristics, now these are going to be clustered by school and neighborhood themselves. Some neighborhoods are more affluent than others, so they on average have higher scoring kids, higher percentages of fathers who stayed in education. So we're going to explain away not just student differences, but neighbor differences and school differences as well. Garner and Raudenbush fit exactly this model, but with more factors. Okay, this is pretty much the first cross-classified application in the literature. So it's kind of a nice one to pick for that reason. So here we get the coefficients in red. They're both positive significant coefficients. When the dad stayed in school past 15, the child would score a quarter of a standard deviation higher at age 16, all else equal. And we can say that because the outcome standardized in Z school, and this is a dummy variable. So that's a really big effect. Harder to interpret age 11 reading score, which is the year 7 reading score, because that variable was not standardized. So you'd have to kind of do a bit of manipulation of that number
to add meaning, or just standardize it before you put it into the analysis. Would be the easiest thing to do. But look at this, the school variance. Look at this. Again, this is too much. This is too good to be true. Okay, look at the school variance, and that comes from knowing the literature. Exactly. The more you know the literature, the more you can sense check, are my numbers kind of plausible. Here, the school variance, as well as being looking kind of, perhaps too small, it drops to effectively 0 off the back of 2 covariates. Okay, and so from a value-added perspective, that would say schools do not vary in quality at all. All schools in Scotland are identical quality. Okay, because we've adjusted for baseline differences by these factors, things that differ between secondary schools on day 1, and then there's no subsequent differences in age 16. It's not right. Okay. The neighbourhood variance also plummets as well. So these percentage drops in the point estimates are way too big to be plausible, personally. Okay, I mean, it certainly suggests that there's wide baseline differences. I think we can agree on that, but not to the extent to which there's nothing going on beyond that. And then finally, there's a kind of a neighbour deprivation goes in. The more deprived the neighbourhood, the lower the score we expect beta 3 to be negative. That's just to illustrate a neighbourhood variable going in. And that indeed has a negative coefficient. But again, I don't think that variable is standardized. So you can have to do a bit of work to get a meaningful effect size for that. You could just standardize the variable before entering it. Finally, what is kind of worth doing is you should continue to always check, do I still need a cross-classified model? And some more variables. Do I still need it? Here, what it's suggesting is in the final model, the neighborhood variance is so small and imprecisely estimated that if we took it out of the model, we'd have a more parsimonious model. It would fit the data worse, but not significantly worse. We should go at that point to 2-level model students within schools. So sometimes when you put an explanatory variable, so it explained away the initial variance for one of these levels, and you can simplify the model at that point. But again, not trustworthy, these results, because they're very small scale. That's it. You can do them very easily in R. You can do them very easily in Stata, as long as at least one of those 2 higher levels, schools or neighborhoods, has a limited number of categories. You can additionally do random interaction classifications. We're really interested in interactions and intersectionality in general, but people haven't really done it with in the random effects setting quite like this. So that's quite an interesting methodological direction to go in. You can add random slopes if that's your thing. You can add additional classifications for school districts, families, and so on. The models can become computationally challenging to estimate, less so perhaps in R. That's it. So hopefully that's kind of interesting and opens up a wider set of models you can estimate. And I think that's it. God.
Next time, 2 days.
Blimey, yeah. Well, okay, that's why I dropped one of the topics. Okay, you're almost there we're on the desert island. So you're trapped, you're marooned in my desert island. It's quite, it wasn't that sunny outside before, was it? But it is. Okay.